Hello, Professor Vedral, can you hear me?
I can hear you.
Okay, thank you. Start or yeah. Okay, I think we can start now. It's my honor to introduce Professor Vlatko Vedral from University of Oxford, who is our speaker today at the International Year of Quantum Colloquium. Uh, Professor Vedral, as many of you know, is a very distinguished physicist. He obtained his PhD from the Imperial College London. After holding many prestigious positions, he is currently a professor of quantum information science at the University of Oxford. Apart from writing several hundred scientific papers, he has authored many technical and popular level books. He has been very active in making technical topics accessible to a general audience. His most recent book is Portals of a New Reality, 5 Pathways to the Future of Physics. Professor Vedral has received many awards and honors. In particular, he has been awarded the Abdus Salam Award, Royal Society Wolfson Research Merit Award, and many more. He is also a fellow of many societies. Today, he's going to speak to us on a very interesting topic: no collapse, no quantum jumps, and no observers, universal quantum physics and how to test it. So, Professor Vedral.
Thank you very much. Thank you for this great introduction as well, and it's a great pleasure to talk to you. I'm really honored to be invited. So the topic will be about fundamental physics, and I think the progress in quantum technologies, which has been incredible in the last 20, 30 years, it seems to me has now brought us to the level where we could really start to probe some of these fundamental questions. And again, to a physicist, this really is the most exciting path to explore. So just to take you back in time, the quantum physics can be seen as a unification of waves and particles. Obviously, this wasn't immediately clear in 1925 when Heisenberg wrote that famous paper that's of course now taken as the ground zero, so to speak, of quantum mechanics. But ultimately, I think this emerged as the best description of everything, and that's what I want to mention here. And of course, as soon as you form this picture of reality that I'll be advocating, it immediately informs you about what you think should actually and could be tested in the future. And I think we're really on the verge of resolving a number of things that people have been discussing in the past, and I'll tell you a little bit about a few of them. In the early days, there was this. This was maybe in the late 20s, very, very soon after the advent of quantum mechanics. There was this question, which is to explain how if everything really behaves in quantum mechanics like a quantum wave, obeys quantum systems, obey the wave equation, if you like, and they behave experimentally like waves, as we know. Then the question is, why do we sometimes, under some circumstances, really see things behave as particles? And there was this very famous Mott problem. It's attributed to Mott ultimately, although there have been many people that have actually suggested a resolution to this. So it's simply to do with the alpha particle decay, which is the left picture here. So when a nucleus decays and it emits an alpha particle, two protons and two neutrons, right? Basically, what happens is that each single run of the experiment really records a straight trajectory that the alpha particle takes in this cloud chamber. So it ionizes the atoms as it hits them, and this ionization leaves a trail, a little bit like airplanes leave the trail of condensation in the sky. That's kind of the microscopic version of this. And the question was if quantum mechanics really claims that even alpha particles, even though traditionally people thought of them as particles, if they really should be thought of as waves, then why don't we get the image on the right-hand side? Why don't they look um, like um, like the usual wave that's expanding from a point of emission of the alpha particle and then isotropically in all directions, as you would expect it? And like I said, this led a number of people to suggest a solution. And it seems to me that this way of thinking about it is the best way to think about quantum mechanics. It's the most consistent one, and certainly all the experiments so far that have really confirmed quantum effects at many different levels, in fact, and we are going into the more and more macroscopic direction, they all suggest to us, it seems to me, that reality really is, at least at the level that we have tested so far, of this type. And that's what's really interesting. So we have people like maybe Darwin, Charles Darwin, the grandson of the famous Charles Darwin, but this is the Charles Darwin, the physicist, was maybe the first person to suggest an explanation. Then Neville Mott, and I think we attribute it to Mott, and later Schrödinger. The title of my talk is almost taken verbatim from a lecture that Schrödinger delivered in 1952. And in fact, he outlines a version of reality that I think it seems to me is the most appropriate one. Again, given all the evidence that we have and given all of the consistencies that we have to obey in physics, and I will touch on that later. So basically, what did they say? Well, they said that alpha particle really does get emitted in all directions at the same time. It really is a spherical wave. And then you have this famous thing that we would now call decoherence, effectively, which is that the first atom that it hits in one direction and ionizes it, it acts like a measurement. And then you can calculate the probability that the next atom that the alpha particle will hit will be in the same direction as this first atom. And indeed, the probability is very close to a unity that this will happen. The difference that all of these people suggested, Darwin and Mott and Schrödinger later, is that actually this happens in all branches at the same time. And that's what's interesting. So this is what you might call the early versions of what we now know as the many worlds interpretation. So basically, these people wanted to be fully consistent. They wanted to describe everything quantum mechanically, and this includes not just the alpha particle itself, but it includes all of the environment, all of the particles of the gas that's ionized and that actually gives us the measurement record, if you like to call it like that. But in fact, there is never any collapse in this picture. This is just an interaction of two waves at the very simplest level, if you like. One wave simply corresponds to the alpha particle, and the other wave corresponds to the background gas. Of course, the story continues then. You can say, what about the photographic plate ultimately, what about the human that looks at it, and so on. And I think Schrödinger outlines in this lecture that I mentioned, which was discovered, I think, in the 90s, quite late. And in fact, people realized that before Hugh Everett even advocated the many worlds, Schrödinger advocated it in a way, I think, in a way that's even more accurate, that's closer to the spirit of what quantum mechanics is all about. So how did Heisenberg do it? Heisenberg had an ingenious way, and it seems to me that this prescription still has a long mileage to go. And in fact, that's what I'll be advocating, that in many ways, Heisenberg's revolution is unfinished. We haven't really applied it to everything that we ought to apply it to, and that's exactly what we need to test. Is nature the way that was imagined in these early days of quantum mechanics? So Heisenberg had this ingenious idea um, to say that classical dynamics is not at fault. Remember, he was trying to explain atomic spectra and why atoms only emit certain frequencies and not the full continuous range of frequencies as you might have it from various classical models of interactions of light and matter. And here is a very simple example, which I think will be useful in talking about the alpha particle, which Heisenberg also beautifully discusses in one of his early books on quantum mechanics. So Heisenberg says, listen, if I'm going to talk about a free particle, let's think about a free particle. It's the simplest example I can think of. Um, if you think about the position of a free particle at some time t, then classically, this is just simply Newton's laws, if you like, when there is no force. Classically, it's equal to the initial position plus whatever is the advance velocity times the time. And now what Heisenberg says is there's nothing wrong with this equation. What is inaccurate, what is incorrect classically is that these numbers, classically speaking, cannot remain ordinary numbers. Dirac called them C numbers, classical, the real numbers. They cannot be real numbers. If you want to describe nature accurately, you have to upgrade them to Q numbers, to matrices, to observable operators, if you like. And Heisenberg apparently did that very naturally to account for spectra without even really knowing that there is such an entity called the matrix. I think it was Max Born and Pascual Jordan who actually wrote the subsequent paper saying, well, these entities exist and they are called matrices. So now what is interesting when you substitute a matrix for X and for V for the velocity, it would be momentum ultimately, P, that becomes a Q number, a quantum number. If you look at the commutator, if you take the commutator of both sides with respect to the initial position, you actually get from the uncertainty relation this quantity on the right-hand side, IH bar T over M. And because the commutator implies that the dispersion in the final position times the dispersion, this is the uncertainty principle, but in time, applied to the position at time t times the position at time zero, must be according to this logic. If your position and momenta are q numbers, then they cannot be, then the positions at different times cannot be specified to an arbitrary accuracy. And you can see that the position at the later time t scales inversely with the position at the initial time. So that means, of course, the better you know the position at one time, the less you will know it, the less you'll be able to specify it in the future. So Heisenberg applies this to the alpha particle. And he says the alpha particle initially, from this point of conception, emission, does spread in all directions. But as soon as it hits the first atom, this localizes the alpha particle roughly to the size of this atom or molecule, in this case, that it gets ionized. So effectively, you've simply localized the particle better. And now, according to this logic of Q numbers, it will start to spread again until it hits the next particle, which then localizes it. So it's this rapid, if your gas is very dense, you'll be having one scattering after another in a rapid succession, which gives you this illusion, if you like, that the particle follows a straight line. But actually, it follows all the paths simultaneously. And notice that in this, why am I saying that there are no collapses and nothing of that kind? Because all you need to discuss is really what happens relative to this ionization of molecules in one branch. But actually, all of these branches happen simultaneously. All of the Q numbers always exist. So it's simply absurd to say that when you make a measurement, you've collapsed the Q number. Q numbers are always there. You cannot destroy a Q number in the same way that you cannot destroy a position of a particle in classical mechanics. So there's nothing you can do to a particle to annihilate. You can change the position of a particle, but the property of having a position is always there. It always pertains to the particle. And that's true in quantum mechanics as well. The underlying reality, the Q number based reality, is simply always there. And this seems to me to be the point that many interpretations, in fact, almost all our interpretations, miss. And I think that's kind of, in a way, what's been holding us back. In addition to of course, having the right level of technology and the degree of sophistication to be able to test these effects. So here is a brief summary of that. That measurement, according to this, and I think Schrödinger was the first person to say this extremely clearly, the very famous Schrödinger's cat example. Experiment, of course, at that time, I think Schrödinger was probably thinking that this is absurd. And then, like I said, 20 odd years down the line, maybe less than 20 years down the line, he changed his mind and he said that's exactly how it is. That in fact is the most accurate account, that everything is ultimately a quantum mechanical wave. So measurement simply is a creation of entanglement between an observer and the system. And the reason why I'm arguing always against the special role of observers is I think that the only consistent way of accounting for everything in quantum mechanics is to acknowledge that observers are just other quantum systems. They are nothing special. As soon as you classicalize your observer, as soon as you insist that an observation has been made irreversibly, that it can never be undone, and it's a fact for everyone in the universe, you've committed a mistake. All quantum paradoxes, apparent, there are no real paradoxes in quantum mechanics, but all apparent paradoxes, EPR paradox, you name it, anything else that follows, is simply, I think, a mistake in people making a boundary between the quantum and the classical world. And in this picture, there isn't a classical world. There is a good approximation to classical reality, which works for all practical purposes. But if you stubbornly really insist that it's classical through and through, you will always arrive at some kind of paradox. You will be contradicting all sorts of things. So that's kind of the main message. And this gets rid of all of these discontinuities, quantum jumps, no spooky action at the distance and so on, no collapses. And Schrödinger was very happy that these are the consequences. He had some very famous, strong statements where he said, if quantum jumps turn out to be real, then I'd much rather be a plumber than a physicist. And actually, there is a lot to be said about this statement, because we physicists really all believe in some kind of reality that makes sense. And to him, what that really meant is that we have to acknowledge that it's the Q numbers that are the basis of everything. And as soon as you make this change and you attribute Q numbers to everything, suddenly reality is perfectly consistent and it makes sense. So now, the interesting, again, I very briefly mentioned this, but classicality very naturally arises out of this. And it really is just very much like in the Mott scattering problem of alpha particles. Classicality emerges within a subsystem simply because that subsystem is very strongly entangled to the rest. It's measured, if you like, or it's been measured continuously or discretely enough in the sense that these discrete events are very close to one another that they give us some kind of illusion of continuity at that level. So we can account for this, and so it's an interesting twist that classical physics is the way it is because ultimately the whole universe is quantum mechanical. So that's in fact the right way logically to speak about this, rather than how we teach this and how we end up doing this, that we start with classical physics and then we put hats, upgrade certain entities, much like Heisenberg did, into quantum entities, and then we proceed. That's logically the wrong way around because nature surely doesn't do it like that. I think nature is quantum through and through. And then we realize that at some level of complexity, quantum features are just they're there, they can never be destroyed, but they're just extremely difficult to uncover because of the complexity of the system. And I think it's that seems to me to be the most logical account of everything. Now let me press on with this a little bit because this is how Dirac came to talk about these quantum numbers. I think as soon as Dirac saw Heisenberg's paper, he understood what was going on, and I think he understood better than Heisenberg actually. Just like Born and Jordan understood it better in some sense. Heisenberg really, because he was the first person to make this breakthrough. The paper, if you read it, is extremely confusing and it's very difficult to understand. But if you take this Q number based reality as what he was trying to really achieve, then I think it becomes much clearer. Dirac was attending courses on all sorts of non-Euclidean geometries as a student in Cambridge. So he came to this with already an interesting bias. He attended a lecture course where he heard that if you describe a straight line, if you write down an equation for a straight line, which by the way is the same equation as the equation that a free particle describes when there are no forces acting on it, it goes in a straight line. However, if instead of the straight line being characterized by numbers, x equals 5, y equals 6 coordinates, and so on, if you think of these as matrices, then suddenly you get geometry that's very different from Euclid's geometry. And in fact, the infamous fifth postulate of Euclid, that if you have a straight line and a point outside of it, there is only one other straight line that goes through this point and it's parallel to the first line, this fails in non-Euclidean geometry, as we all know from general relativity. But the interesting thing is that it's these kind of ideas that influence Dirac, who immediately recognized what's going on in quantum mechanics. So it's very interesting that in quantum mechanics, we also violate non-Euclidean geometry. You see, people keep saying that quantum mechanics is so different to general relativity that it's hard to imagine how to unify them. And I completely disagree with this statement. I think they're so similar that actually it's remarkable how they're telling us about many things that they have in common. And this incidentally requires a completely separate talk, and I'm not going to talk about this at all. But I think the story is much more interesting than what many people lead us to believe. So now what's interesting is think about two alpha particles being emitted. So they're really spreading according to this Q number based logic. They're not really going in parallel, even if you send them initially in parallel as you can quantum mechanically, they are actually going to diffuse, if you like, the way packets are going to spread. And now what's interesting is that if you add interaction to this between the particles, then the question is how must one phrase this interaction in order to comply with this Q number based reality? And I think this leads us to some of these ideas that I think would be the most exciting to test with the technology that we have. And they can be tested in various domains. In fact, I will only go in one direction really in this talk, but I think they can be tested in many domains. for consistency reasons, and that's what I'm saying in this slide, it seems that the mediator, if you really want to mediate between all of these possible locations of each of these particles simultaneously, and it seems that that's the only consistent account of the forces between different bits of matter, let's say in this case, if that's what we are discussing, then and you can think of in terms of information. I think this is a very helpful way, and that's where I think quantum information has taught us a great deal in the last 50 years or so. That if these quantum systems like alpha particles have a certain capacity to process information, and they can be in these superpositions as they propagate, then if you really want to mediate the interaction properly between them, whatever mediates this, whatever channel you imagine they have to exchange this information, it must also be quantum. A classical channel simply doesn't have the capacity to properly mediate all the quantum information between genuinely quantum objects. And so the question I'm asking here, is this the whole story? And of course, no one knows. But I think that's the beautiful thing to test. This, to me, is exactly what should be suggesting to us the experiments that we ought to be doing. And obviously, to a physicist, the first question is gravity. And I think that's the outstanding force. And in fact, people even argue whether we should be thinking of gravity as a force. That there is a multitude of views on this. But the question is, should gravity and can gravity be brought into this kind of framework that I'm advocating here? And so let me tell you a little bit about this because it's an interesting story. The key principle in Einstein's gravity is the equivalence principle. So you can think of almost you can think of general relativity as telling us that the world is locally Minkowski. Everything behaves according to special relativity in tiny volumes, if you like. If you do your experiment and you don't really make a very extended experiment spatially, then, and that was the happiest thought of Einstein's life, as he's called it, then if you are falling in gravity, he imagined if you are in a closed lift, you can't see anything outside. Then if you're falling in gravity, you are actually an inertial observer because everything close to you also is falling at the same rate, and everything behaves as though it's just simply stationary around you. There are no forces. By falling in gravity, you effectively cancel gravity, if you like, and you become an inertial observer. So this is very distinct to how Newton thought about inertial observers, that they must move at constant speeds with respect to one another. So this is this famous equivalence principle. And now, of course, many people claim that quantum mechanics will be problematic when it comes to the equivalence principle. And the question is, if you have a mass in a superposition of two different accelerations, so now we know that in quantum mechanics, you could actually, if you can fall at one acceleration and you can fall at another acceleration, then quantum mechanics says that there is nothing in principle that should stop you from making a superposition of these two. And what does that mean now? And many people advocate that something will fundamentally go wrong with quantum mechanics. Something must collapse to decide which of these two alternatives are correct. And I think the exact opposite. In fact, I think that the equivalence principle can be beautifully absorbed into quantum mechanics, but you really must think of everything as being made up of the same stuff, of the Q numbers. And I think it's fully consistent. It's as consistent as any other symmetry. Energy conservation, momentum conservation are absorbed into quantum mechanics in the same way as what I'll be advocating now, the equivalence principle should do. So I'll show you a beautiful experiment that my colleague Ron Follman executed recently, which is exactly to test what happens when you superpose two different states of motion. And this is really to do with a very simple problem of quantum free fall. So you have a Hamiltonian of a particle which has a kinetic energy. It has this potential energy mgx. Imagine in Earth's gravity, but of course you can apply this to more complicated scenarios. And the question now is what happens to this? So I wrote extensively about this. It's a very easy model to solve analytically. I don't want to really bore you with that too much. But the experiment that Ron did reminded me very much of the Galilean experiments. Of course, Galileo was dropping all sorts of objects down inclined planes, even from as people say, from the Leaning Tower of Pisa and so on, and observing how they fall. And he's the first person to understand motion and gravity the way that classical physics later formalized it fully. So here the question is, what if I really could I measure what happens to this accelerated particle? And it's interesting that the accelerated particle in quantum mechanics, in addition to the wave packet moving in the usual classical way, that the center of the wave packet simply moves at the rate that you would expect a classical particle to get accelerated with this extra gt squared over 2 term, there's an extra phase in front of this, which is precisely the effect that you get in quantum mechanics, which is an additional term that doesn't exist in classical physics, in fact. And the question is, could you observe this phase? And of course, if it's a global phase, you cannot observe this extra term. It goes as this t cube term that I mentioned it here. But if you have a reference, if you make a superposition of your wave packet so that in one reference frame it's stationary, it doesn't accelerate, and in the other reference frame it really is undergoing a ballistic motion in Earth's gravity, then you can interfere these two possibilities and you can see the shift in your fringes, if you like, as the result of this relative phase between the two. So now what was a global phase for the single trajectory suddenly becomes the relative phase between two different accelerations. In this case, it's even simpler because one trajectory is accelerated, the other one has zero acceleration. That's kind of a special case. And Ron Follman and his group did an experiment on a chip. He literally launched a Bose condensate on this chip. It was all done on a very tiny dimensions, a very tiny volume, if you like. And the condensate was split into two. This one branch of the red branch here was kept at the constant velocity, if you like. It was stationary in the lab frame. And the other branch then was simply accelerated in Earth, and then the two were finally interfered. And so what's interesting is that this experiment confirmed exactly this t cubed contribution that arises due to the accelerated motion and this extra phase that you have in quantum mechanics. And in fact, nothing weird happens in that experiment. There are no collapses. So the fact that we have the equivalence principle is explained in the way that each of these branches, exactly how Mott and Heisenberg and Schrödinger and Darwin and everyone else I mentioned would have thought about this, is that in each branch of the motion of this condensate, you have locally to that branch, the equivalence principle is obeyed. So in quantum mechanics, whenever you upgrade any classical symmetry, like energy conservation, in quantum mechanics, this becomes a branch by branch. In every branch of your wave function, things are conserved exactly. So that's another mistake that many people make, that they claim that conservation is stochastic. It's statistical in quantum mechanics. Sometimes you get more energy, sometimes you get less energy, but on average, you get the same amount. That's untrue. That just simply cannot be right. This would mean that energy conservation is actually violated. It's just correct on average. What I'm saying, quantum mechanics is telling us, and it seems all our experiments so far agree with this, is that it's strictly conserved. Everything is strictly conserved. All principles. It's just you have to think of them in branch by branch, just like the alpha particle experiment. They really are just different instances of the same kind of thing. Now, of course, what we haven't tested, there is much more to go beyond to test. And there are beautiful ideas in this direction. And I think we are much further away from testing this simply because the numbers happen to be very small. And I think we're experimentally still far away from some of these. So if you think of the background field, if you take the electromagnetic field in which this experiment takes place, then there are various people like Unruh and Paul Davies and many others who actually have said that acceleration will transform the vacuum differently, and you will be able to see. So basically, what appears to be the vacuum for an unaccelerated observer suddenly appears to be full of quanta for an accelerated observer. And what this suggests, if you take this Q number based reality seriously, is that one acceleration will be entangled to one kind of vacuum, and another acceleration would be entangled to another kind of vacuum in quantum field theory. So if I don't just look at this, the system that interferes as quantum mechanical, but I quantize the relevant background, the field in which this takes place, then what some of these accounts are telling us, again, we don't know if this is the right way to do these things. We ought to be testing this, is that these two vacua will be different. And if you make the difference between these accelerations big enough, now the formula that I'm giving you, I'm assuming that one of these accelerations is zero, like in the experiment I showed you, and the other one is A. If you make this acceleration big enough, you will actually see that the two vacua become more and more orthogonal. In the experiment that Ron did, the acceleration was, of course, Earth's gravity was tiny compared to the speed of light cubed here. So basically, this exponent was effectively equal to 1. The two vacua are nearly identical in that experiment. The difference is so small that you can really not detect this. However, if we manage to control these kind of superpositions of bigger and bigger differences in accelerations, maybe one day we'll be able to test something of this kind. So the question is reality really of this type? In which case, notice that there is still no collapse of the superposition, but what simply happens, and I think that's the right way to think about this, is that there is entanglement being created between your matter wave in this experiment, the Bose condensate, and the background field. So this is really the summary of this. And then, of course, the thing I want to mention before I really conclude, so this is just really a summary that the equivalence principle, returning to gravity, should be phrased in a way that if you have a mass in a superposition, and if you have a test particle, and if you ask yourself, how is this test particle, which is initially localized in one place, how will it respond to a massive object being in a superposition, then this kind of picture, which Bryce DeWitt called totalitarian property of quantum mechanics, that it should really be applied to everything in totality. It's the only consistent way. And then it simply says that the mass will be simultaneously accelerated. The test mass must be simultaneously accelerated towards each of these locations in the superposition of the first superposed mass. And it seems to me that's the only consistent way we have at present to account for both quantum effects and Einstein's principles from general relativity. So that's kind of an artist's impression of what's going on in this picture. And so this led several people, I think Sugato Bose, a friend of mine, a colleague of mine from University College in London, and Chiara Marletto and myself, a few years back, we actually proposed what I was already indicating a long way before, actually, and I can show you that slide here, to try to see whether gravity really acts in this quantum mechanical way by having two masses in a superposition each, much like in this picture, actually, and then seeing whether these two masses could get entangled through gravity that is the mediator in this case. And so we published this a couple of papers on this, which basically suggests that if you could do these experiments, it's a double interference experiment. Each of these masses is put in a superposition initially, then they simply couple through gravity, and then what you do is measure them at the output, and you effectively test something that's very much akin to the violation of Bell's inequalities. You just must apply one of these witnesses of entanglement to confirm that the masses are entangled. And then if you really are certain that gravity was the only mediator in this case, and it acted locally and then propagated between these masses, then the only conclusion is the gravitational field must also have quantum mechanical degrees of freedom. Otherwise, you couldn't entangle quantum objects if the mediator is of purely classical nature. And so now I think we have a number of these experiments that are being done. And of course, the difficulty really is to put massive enough objects. I want to give you just a rough idea of this without giving you too many details about what's going on. But if you take a mass that's roughly a nanogram, which is still a very big object to control coherently, and if you can make the superposition such that the two interferometers are roughly microns up to maybe 100 microns distant from one another, and you keep this going for about a microsecond, then you can actually get the maximum entanglement between the two masses. So this is kind of the best case scenario where you start with two superpositions which are not entangled at all initially. Then you let the gravitational interaction take place. And then the final interference that you perform on these masses should reveal to you whether they become entangled or not. And I think in this formula, I'm assuming that the phase kick is maximal, it's pi, so that the state ends up being really a maximally entangled state that I wrote here at the bottom. But obviously, when you do experiments, you will have all sorts of other sources of noise. And depending on the resolution that you can achieve, and remember, our metrology now helps because it's getting really better and better through our quantum technologies. Maybe even a fraction of this phase, let's say 100th of the phase, will be sufficient to in fact give us this gravitationally induced entanglement. And this is hugely exciting because, so that's maybe the last thing I want to mention. This is hugely exciting because, first of all, notice that in the past, people would have always talked about the Planck mass as possibly the size of the system where gravity starts to behave quantum mechanically. And that's some 4 or 5 orders of magnitude bigger than this mass here. So so this experiment tells us that we actually don't have to go to masses as big as that. And we could indirectly still get some indication whether at least some gravitational degrees of freedom are quantum mechanical. So this is very nice because it would help us discriminate between two big categories of theories that account for gravity, if you like, in quantum mechanics. And I'm here bunching many different things under the name of canonical. Canonical just means we really do want to treat gravitational field quantum mechanically, whatever you decide this might mean. And there is a bunch of very interesting discussions to be had there. But all of these approaches at this lowest level of approximation, the weakest, the first order, so to speak, approximation of Einstein's gravity would in fact agree that entanglement should be created between these two masses. So they would pass the test, if you like. On the other hand, would be all sorts of collapses where people believe that gravity will genuinely destroy quantum superpositions in an irreversible way. All of those approaches, as far as I'm aware, would be betting on the fact that gravity cannot entangle masses in this way. And this also goes for this quantum field theory in curved space, where basically you acknowledge that all fields are quantum mechanical, but they're still sitting on the classical gravitational background. In this case, also this kind of approach, one might call this a semi-classical approach, wouldn't be able to account for the generated entanglement. And in a way, this goes back to my earlier comment, as I said, that as soon as you sneak in classicality anywhere in our account, my feeling is that you're going to go astray. Something will happen that will lead us to a paradox, if you like, an apparent paradox. So the only way to avoid any of these issues is really to treat everything ultimately quantum mechanically. It's the best account that we have. Obviously, experiments of this kind may even lead to another possibility, which is that we have to supersede both quantum mechanics and general relativity. That's definitely not out of the question. So if you think about things like maybe string theory is the only thing that comes to mind at the moment. String theory certainly at the lowest level of approximation will actually lead to entanglement generated between the masses. However, what we don't know, of course, and it reduces in one limit to general relativity, in another limit to quantum mechanics, but it's a bigger overarching theory. So that's yet another possibility, and we may well discover as we go down this road that that's exactly what's required. And in a way, it would be very similar then to the revolutions we had in the past, where simply the previous theories were in fact unified, just like the Newtonian theory and the wave theory of Maxwell, let's say, were unified through quantum mechanics, that ultimately everything became of the same quantum mechanical type. And it could be that that's what we are facing when we are quantizing gravity. But unless we start doing these experiments and go down this road of testing all of this, we won't know, of course. And luckily, like I said, we now are in a great position to do that because of the huge progress in quantum technologies. So one of the last slides, just to actually zoom out a little bit and show you how little we've actually tested in this domain. So this is this famous physics cube where you have Newton's constant gravitational in one direction, Planck's constant in the other one, and inverse speed of light. The reason is simply because when c goes to infinity, I would like to recover classical mechanics at this vertex here. And when g goes to zero and h bar goes to zero, whatever that means, I'm oversimplifying, obviously. then you get this classical mechanics. So the thing that we really have tested, like if you want to test all of these things simultaneously, you are at this vertex, which I labeled as the theory of everything. Whatever, I'm not even sure I necessarily believe that there is such a thing, but it's kind of the first thing that comes to mind. So that would really unify all of these things. We certainly have not tested anything in that domain. The domain that I'm talking about really is non-relativistic matter somehow possibly coupled to quantum gravity. So basically, G matters certainly. H bar does matter, but the speed of light is irrelevant. Matter is not really moving at relativistic speeds at all. So even in this direction, we have a lot of mileage. So I'm talking about this vertex of the cube here. There is this vertex that we should be testing more as well. And then, of course, hopefully these two will ultimately converge onto this vertex. But along the way, as I said, we may discover that there is a lot more to this story. And obviously, with the new developments and the new theory, this opens up, as always, a whole new a line of experimentation as well. So who can tell, really? And final thoughts before I stop. The big statement here is that all apparent paradoxes in quantum mechanics come from a hybrid, from a dualistic, if you like, description, where half of the experiment we are talking about is quantum and the other one is classical. And this leads us to all sorts of mistakes, wrong inferences, I think, wrong conclusions, and claims that there is something wrong with quantum mechanics. And my claim is there is nothing wrong. Certainly at this stage, I don't know if there will be something wrong in 10 years' time, but certainly now there isn't anything. The only way to even mathematically consistently account for all of the symmetries is to really treat everything quantum mechanically. The system and the environment, which includes everything else, must be quantized. Otherwise, it's very difficult to preserve the exactness of these symmetries. So this is a little bit more of a theoretical reason. The first point was more about how to account for all the experiments so far. The second point really is that even theoretically, the hybrid picture is not really consistent. It just doesn't tell us properly how to absorb classical, so to speak, symmetries into quantum mechanics. And the exciting thing, the final point that I want to communicate is that it seems to me that the next 2 to 3 decades of science will really be defined by this um, um, basically fact that quantum mechanics will be leaving the microscopic domain where it's been tested so far and it's been 100% accurate over the last 100 odd years, and it will be going into the more macroscopic domain. Gravity is just one of these things. There's, of course, chemistry, biology, and going even beyond. And as we already heard, by a complete coincidence, today is the publication of my book, where I actually do talk about all of these portals that I think are extremely interesting to us. And if you're interested, have a look at it. And of course, I discuss things in much more detail than during this talk. Thank you very much for your attention.
I think let's thank our speaker for a very illuminating and entertaining talk. So now let's see if there are any. No, sir. You can go on.
Hello.
Hello.
Yeah.
Sir, I just wanted, yeah. Uh, Good evening, sir. I just wanted to ask, is the non-commutativity of X and P is preserved in quantum free fall? And if it is not preserved, then how does it conflict with the local flatness in space-time?
It's a great question. Actually, this is a very profound question that you are asking. Um, Already, when you look at what I was saying Heisenberg did in that equation, you have another parameter which is time, which he didn't quantize. It basically was sufficient to just quantize x and p. And what we learn in field theory then is that you have to dequantize space and time in order to treat them on an equal footing. Of course, there are approaches as well which insist that you should continue and quantize even space and time, and there are all sorts of non-commutative geometries. So this is a completely unresolved question. When I think about the experiment that I showed you that Sugato and Chiara and myself suggested, it's completely sufficient to really model the gravitational field just like any other field. So we're thinking about G mu nu, the metric simply as the vector potential in electrodynamics. And if you quantize that in the same way, so you're leaving the background space-time completely classical in this approach, and this suffices. I think it's the approach to quantizing fields that's been advocated by many people. Certainly Feynman did it, and Bryce DeWitt, and so on. There is a school of thought that we ought to treat gravity in the same way. But I think other approaches, as you now rightly pointed out, would agree at this level too. I think if you quantize space and time, and so to me this is a beautiful question because um, I think we should be asking how to discriminate between these two approaches. And actually, I have no idea how to do that. I think this is one of the key. If you want to now go beyond and you say, okay, you've confirmed that some aspects of gravity are quantum mechanical, but can you tell me which aspects are quantum mechanical? Then this experiment doesn't tell you anything actually. So I think that's something I'm intensely thinking about now. It'd be great to have an answer to this.
Okay, thank you, sir.
Thank you.
Questions on the chat box. So can we discuss? So I think one question is, can we discuss the implications of the many worldview on probability and branching universes and how it derives the Born rule without additional postulates?
Excellent question. That's an excellent question. In my book, I in fact criticize the many worlds as well, in the sense that it's more about the name that we attribute. So my view is that we should get rid of all of the classical remnants within quantum physics, and of course, our language frequently prevents us from doing so. So many worlds suggest that there are many classical worlds, but they all exist in a superposition. But this is just a special case of quantum mechanics. In quantum mechanics, you can have states that are not fully distinguishable. You can have distinguishability going all the way from 0 to 1 to maximum distinguishability. And only this limit, when things are perfectly orthogonal to one another, you actually get what we call possibly some superposition of classical worlds. But even this is wrong, and I'll tell you immediately why it's wrong. In fact, one of my chapters in the book, one of the early chapters is precisely on that, is because in principle we can interfere them. The worlds may be remain distinct only for all practical purposes. So maybe they become so different to one another that it's extremely difficult to bring them back to interfere them. But in my view, this is simply just a practical limitation. In the same way that Newtonian physics is basically reversible, but in many practical instances, it will be irreversible because we are not going to be able to keep track of all the collisions of all the atoms and so on. It's the same story in quantum mechanics. The things are only irreversible for all practical purposes, but they never really are. You can always, in principle, unite these things, in which case, when you interfere them, they automatically stop being classical. So I think even the many worlds name is not really accurate. So now the real question that you ask is how to understand probabilities. And I think probabilities simply emerge in this classical limit. I think anywhere um, in between this maximum distinguishability and zero distinguishability, probabilities are of very limited use. In fact, it's inaccurate. You must always remain at the level of amplitudes. So, in some sense, at some level of coarse graining, probabilities emerge as it really is an emergent notion that becomes useful in that domain, and it can be justified in a number of ways. But by and large, if you take the most generic state of the universe, I think probabilities are not helpful at all, actually. So it's very context dependent of what kind of entity you want to use to quantify. Ultimately, of course, what you're quantifying is the non-commutativity of Q numbers. You're really quantifying the fact that you can never specify all of these things to an arbitrary degree of accuracy. But I think probabilities, as we think of them, emerge in some limit of this picture. And I think one can argue how to derive them. There are various approaches.
So our next question is, what are the main differences between relational quantum mechanics and other no-collapse interpretations, particularly regarding the role of interactions over absolute states? So this is about relational quantum mechanics.
That's a good question. Actually, it seems to me that this relational view is exactly what Everett himself was advocating. Sorry. It's exactly what Everett was advocating, I think. Relational in the sense that if you ask why do I, when I observe a system in a superposition, why do I see just one outcome? People sometimes mistakenly think that this requires an extra mechanism. But in fact, if you think of yourself and the apparatus that you are using and everything else as a bunch of Q numbers, then as Schrödinger taught us beautifully, what happens really is that your Q numbers, whatever characterizes the observation inside your brain, let's say ultimately, but we don't need to go that far. You can use any other physical system. These Q numbers of the, called it the measure. Like I said, I don't like the word observer because it carries extra connotations. I think observers are just like any other physical system. I don't think we need to go beyond, at least at present, to account for observers. So the Q numbers of the measure get entangled, if you like, correlated with the Q numbers of the system. And that's what leads to the emergence of reality. And it is in a relational manner. But you don't need to insist on getting just one outcome. It's completely okay to keep all of these outcomes at the same time. And then, of course, with respect to one state, one branch, one element, like I said, it's very difficult to describe this with the classical language, but with respect to one of these states of my Q numbers, there will be the corresponding state of the relevant Q number of the system that I'm observing. And that really is all there is to a measurement. You don't need to suggest anything else. So quantum mechanics already answers the question, why we never see a superposition. I think this is a big mistake when some people go around and they say, oh, but we never see a quantum superposition. Quantum mechanics exactly tells us that we will never see a superposition. That's the beauty of it. It already contains within itself, if you take everything seriously to be quantum mechanical, it already contains the measurement, what we call basically the measurement. So it's really because of the correlations that are being made, and because each side, the measure and the measuring, the object that it's measuring, obey quantum mechanics. They are limited by the same uncertainty principle that we actually get classical, what we call classical outcomes ultimately. And that's the beauty of this picture, I think.
So another question is, how does deep coherence theory contribute to universal quantum theories that avoid observer-induced collapse? And what are its limitations in fully resolving the measurement problem?
It's a good point as well, very much related to what I've been talking about as well. So it's very important, as you mentioned now, to discriminate between decoherence that happens in the way that I'm describing it, namely when you have two systems that are entangled, then if they're maximally entangled, then neither of them can exhibit on their own interference effect because they're basically in a maximally mixed state. So effectively, each of these subsystems in a maximally entangled state have become classical for all practical purposes. Like I said, you didn't destroy their Q numbers. They're still fully quantum mechanical. And the way we know that they're quantum mechanical is because if we experiment on them together, you can always do interference and confirm that they are entangled. So that's one kind of decoherence, in which case decoherence is just a word that describes these entanglements, but everything is still fully quantum mechanical. And that's what I'm advocating. I'm very happy with that. However, if by decoherence, and some people mean this by decoherence, if you mean that there is an extra magical classical force, if you like, that causes a genuine irreversible collapse of quantum superpositions, then I don't believe in that. But that's possible. Certainly, logically, it's possible. Although, like I said, it violates all sorts of things like exact conservations, it violates the equivalence principle as well, and almost anything you can imagine. In fact, I think everything would be violated in this picture. However, this can be discriminated, and that's the beautiful thing that, in fact, many experiments that have been done so far, almost every time someone does an interference experiment, what that means is that they've ruled out collapse at a certain level of complexity. I think there are some beautiful recent experiments on neutrinos done at the Fermi Lab, which actually rule out, I think, half of the space of parameters where these collapse theories, genuine collapse theories, have been proposed. So I think sooner or later they will all be ruled out. I think if the gravitational entanglement is induced the way that I described and I imagine, I do not think that a single collapse theory will survive this. I think they will all, I mean, genuine collapse theory, some classical decoherence theory. So I think we can discriminate between these two. It's a very important point that you raised.
Next.
Okay, so there is another question. In Bohemian mechanics or pilot wave theory, how are particles
Yes.
determined without invoking color or observers? And what role do hidden variables play?
Yeah, it's another good point because, of course, we have this multitude of interpretations, and some of them do insist that maybe we shouldn't do what I suggested, which is that we should take. I'm suggesting that we should take seriously the idea that I'm suggesting. Sorry, there's some noise in the background. I'm suggesting that that we should take these Q numbers seriously, but the Broglie-Bohm theory, as you say, suggests that no, we should actually keep the classical view that they are really well defined and they could be defined to an arbitrary accuracy. But the problem then, of course, the price to pay, as we know from Bell's inequalities, by the way, the price to pay is that you must be non-local. You must allow signaling. In fact, you must allow instantaneous. It's not just faster than the speed of light, but it's instantaneous. So to account for entanglement, even of two particles, while insisting that each particle has a well-defined position and momentum, automatically forces you into spooky action at the distance, real spooky action, not what Einstein called entanglement. And in that sense, to me, that's what makes it unappealing. However, if you do allow that, then I think at present you can account for all the stuff that we've been doing, all the violations of Bell's inequalities could actually be explained, if you like, by dropping the postulate that everything is a Q number and simply violating special relativity. And to me, this is also a beautiful point that you are raising. So in addition to what I mentioned, would be nice to know how to quantize gravity. Do we quantize space-time? Do we quantize G mu nu? What do we ultimately upgrade? Here you are raising another question, which I think is beautiful, which is exactly which of the Bell assumptions should we drop. So he assumed the locality assumption, and he assumed what we call the reality assumption, which means that these local hidden variables are really made up of C numbers, as Dirac called. They're real numbers. They are not subject to any uncertainty. And these two postulates are together violated in all our experiments. We know that. So there is little doubt up to the level of some even complex molecules that in fact quantum mechanics simply violates this kind of hidden variable view. However, this doesn't tell us which of the two postulates we should drop. And there are, by the way, many other hidden assumptions that people bring in and other possibilities which are even crazier than violating relativity. So you're right. To me, it seems it would be nice to think. It's a pressing problem to think about how to discriminate between these two. What kind of experiment should you be doing to really convince me that relativity doesn't fail and that it's really the Q numbers that are important here?
The question is, how do relational quantum mechanics or cubism fit into no collapse paradigms, and do they truly eliminate the observer's role?
Yeah, this is a good question. I feel that relational, like I said, I think relational interpretation is simply just a restatement of Everett, and in that sense, I think it does account for the measurement. It has the limitations that I said that I personally don't like, because I think the quantum reality is exponentially bigger than just a superposition of classical branches. I think that's where this kind of relational attitude fails. You can't really apply it to everything. You really must consider the scenario where you've created maximum entanglement between your system and the environment. Cubism, by the way, on the other hand, that you raised, seems to me to be suggesting that um, that the wave function or the density matrix, ultimately quantum states, are really the states of knowledge, very much like we think of phase space in classical physics, that that this is some lack of knowledge on our part, and that the lack of knowledge would explain all of this. And I think this view doesn't work. It falls into the category of the hybrid views of reality that I mentioned, where your observers are really classical and they're doing everything classically. And this view is only possible if your observer never gets engaged with the system. If you really keep these two realities completely separately from one another, then you can have it probably consistently. But as Schrödinger taught us, as I said, as soon as the macroscopic world gets entangled, as soon as it couples to the microscopic world, then all of these superpositions from the micro world infect, if you like, the macro world, and the whole universe then must become quantum mechanical in one and the same way. So I don't think that the quantum Bayesian view is correct. I think it's false as well.
Hello. You mentioned that, we know that violation of Bell inequality actually implies violation of reality, realism, and locality, both of them together.
Correct.
But you said that we can drop one of them and violate. But the essence of Bell inequality is that violation of both of them. So can you please explain, how to conclude that just one of them can violate Bell inequality?
No, what I was saying is that given that either of the assumptions or both logically, so when you violate Bell's inequalities, it could mean three things. Assumption one is violated on its own, assumption two is violated on its own, or both of them are violated at the same time. There is no experiment that discriminates between these views. My personal view is that we violate the classical reality assumption. And that's exactly what I've been advocating. The world is not made up of real numbers. The world is made up of quantum numbers. So that's the axiom I think is violated. There is no reason to violate relativity, the other axiom. The other axiom seems to me to be perfectly well confirmed in all other experiments. There's not a single violation of special relativity in anything that we've ever done so far. So nothing to us suggests that. However, logically speaking, it is possible to invert what I just said and to say that maybe relativity is violated. Whereas reality does stay classical. So it's logically possible that you say, well, the world is described by C numbers, just like in classical physics. This is your de Broglie-Bohm interpretation. But then to account for entanglement, I need instantaneous communication between these classical numbers. And you can do that. It's very easy to come up with a non-local model. Non-local models are always possible to actually explain anything. The trick in physics, I think, and that's what Faraday taught us, is to explain it locally. And that's why he argued that fields are very important to introduce as a communication system between charges for Faraday. And I'm arguing the same for masses, for gravity. But logically, it is possible that the world is communicating instantaneously, and according to Bell, that it's classical, fully classical. So we have no way of discriminating between these two scenarios. There is no experiment so far that tested one of these against the other one. That's what I'm saying. So either you drop reality, which is what I'm advocating, you drop classical reality. I still believe in reality. It's just quantum. These Q numbers are never destroyed. The universe always consists of all of this multitude of Q numbers. And like I said, you don't destroy a quantum number when you measure it. You simply just create entanglements between different Q numbers. But they always exist. Just like in classical physics, properties always exist. You don't destroy a position of a particle. You change the position or you change the momentum, but you don't destroy the property of having a position. And the same, I claim, is true in quantum mechanics. The only difference is that your property is a quantum mechanical number. It's an operator. And that seems to me the best account. But we don't have any experiment to discriminate between should we drop classical reality or should we drop special relativity? Or should we drop both? It's possible to drop both, by the way, and account for these things.
But the experiment still that they considered, they drop both of them, right, together?
No. The experiment logic goes like this. If A and B, you have a proposition A and a proposition B. If together they are falsified, which is Bell inequality, what it means is that the negative of A and B is not A or not B. So that means you either falsify A on its own, or you falsify B on its own, or both of them fail. That's what the or means in logic. So our experiments are not telling us which of these three possibilities are the case. They're just saying together they are violated. But that could be because each is individually violated, or both are violated at the same time. We don't actually know which of these three possibilities is there.
Okay.
Thank you very much.
Thank you.
Now, when you say that the next 3 decades of science will be defined by the quantum physics, going more and more into the macro domain. So we know that the superconducting quantum circuits, that's in the macro, that how large you foresee the macro domains.
It's an excellent, that's the key question, really. Because at the moment, the way I envisage this, and it seems to me it's going in that direction, is that when I say that quantum will go into even chemistry and biology, what I mean is that we will discover that there are quantum effects, much like I think the analogy, as you said, with superconducting circuits is perfect. Because what that means is that there are some degrees of freedom in these experiments which we can really control quantum mechanically. It doesn't mean that you've put the whole superconductor in a superposition of two spatial locations. That's not what we are doing. And in the same way, I don't think that we will be able to take a biological cell and put it in a superposition of two locations. This would be a phenomenally difficult experiment. We will do it. I'm optimistic we will do it one day, even that. But I don't think that we'll be able to do it within the next decade or so. So what I have in mind is that inside some of these relevant entities, like the biological cell, or even inside the mitochondria in the cell, or some complex chemical reactions that are not even inside living systems, inorganic chemistry, we will actually understand them better and better in terms of quantum mechanics. So that's what I'm advocating. Of course, certain things will almost always, I could say, remain outside of that, because the complexity of modeling this exactly could be exponentially hard even for a quantum computer. So if you really want to model all the aspects of a very complex chemical reaction, I think it's unlikely that we will be doing that anytime soon. However, I think what we will be discovering is that quantum mechanics in certain subdomains matters more and more. So I'm very confident that this gravitational experiment will be done within the next 10 years. So that seems to me that we are on the brink of being able to manipulate large enough systems, nanogram or so, maybe 2 orders of magnitude smaller. And I think this will be done. And this will be a milestone, actually. This experiment in its own right will simply be a phenomenal experiment, demonstrating a high degree of quantum control and engineering, and certainly relevant for making large-scale quantum computers. But I think the rest of science will go in these pockets of us discovering more and more quantumness there. Remember, just the last thing to say, if you want to understand even the bonding of two of the simplest atoms, take two hydrogen atoms. We all learned this in our basic quantum mechanics course, how basically they exchange. When they're close enough, electrons can hop between them, and they basically have these extended orbitals, which is really the force that pulls them together. It leads to lower energy than each of the atoms would have on their own. So superpositions and entanglements are key to chemical bonding. And I think ultimately the whole of chemistry will be understood in terms of entanglements rather than this old-fashioned language of what kind of bond. All bonds in chemistry are the same bond. They're all quantum, really. But I think chemists, for historical reasons and for pragmatic reasons, call them under different names. So I think there will be a revolution in our understanding of that. But I think even two hydrogen atoms, if you want to model that dynamically, how they approach one another, how they form these bonds, even this is beyond our current simulation ability. So we are confident that it probably is quantum mechanical in all its degrees. I mean, why, you know, what else could be happening there? However, even this simplest of the molecular bonding is still beyond the full simulational capabilities of what we could do, which is another reason why it would be good to have a quantum computer, of course.
Okay, thank you.
Thank you.
So I think we had some very interesting session, and I think we have lined it out. So I think let's thank our speaker for this wonderful time.
Thank you very much. A great pleasure. Thank you.